the lecture on characteristics of the stepper motors of special electrical machines. Here, here if you observe, these are the characteristics, contents we are having that static characteristics of a stepper motor, dynamic characteristics of stepper motor, open loop control, closed loop control, and microprocessor based control. For any motor, if you observe, for any motor, there are four quadrant of operations. Not for the total all the motors, but some of the motors having the applications in each and everywhere. If you consider each and everywhere means if you suppose if you observed any lifting purpose, that is most of the applications are for lifting purpose means generally you are observing that lifts we are placing on the commercial complex and also some of the development cities of apartments like these cultures. Here, the lifts that are working based upon the drive system. Here, that is nothing but a drive. Here, each and every motor that it can be controlled by using a power electronic converter drives which are controlling the motor. Here, at the time of the starting and also at the time of the stopping, in between these, there is an operation that is a steady state operation. These are comes under the static characteristics. Characteristics. But under steady state, under at a stationary condition or the stationary position, or at the time of the start, after the stop, these are the conditions. Next, if you go for the dynamic characteristics, means these are the characteristics which we observe on running condition. Suddenly, if you whenever the motor is to be running, suddenly if the load has been increased, therefore automatically the torque has been increases automatically. With respect to the torque, the current value is also increases. Here, the dynamic characteristics of the motors can be observed here while running the motor. And next one, open loop control, closed loop control. As nowadays we observe that uh, there is a open loop system and also the closed loop system also controlling of a machine. And also now we are using that fuzzy logic and also neural networks. These are the comes out of the microprocessor based, but these are on automatic based automation. Automation has been increased nowadays for all the industries. If you observe, okay, uh, those we observe here. Here, before going to that, some of the definitions we observe of a step angle. What is the step angle? It is the angular displacement of the motor of excitation applied to the stator winding. That is, that is the angular displacement of the rotor. How rotor, if you observe the stepper motor that is having that the stator and the stator is having the permanent magnet poles, electromagnetic poles, and also the rotor is having some of the motors of a permanent magnet, some of the motors are normally silicon steel structure, laminated silicon steel structure of the rotor, and for the stator there is also electromagnetic field. Here, whenever if you excited any one of the phase, therefore the rotor should be displaced from one position to another position. That is nothing but the rotor can change the direction of rotation. Sorry, can change the rotation from one axis to another axis. Means with respect to the stator axis and also the rotor axis, is there any displacement? That is nothing but the step angle. The step angle is the angular displacement of the rotor. The stator is if the excitation is applied towards the stator winding, and it is given by the formula of theta s, that is a step angle. Theta s is equal to 360 degrees by n into nr, n suffix r. In previous classes, we discussed about n, in place of n, we written in the form of m also. That is the number of phases. How many number of phases you are giving, and also how many number of rotor teeth are there. That is also depend upon the angular displacement of the rotor. Angular displacement may be varies. It is nothing but 1.5 degrees to up to 90 degrees also. There is a possibility to rotate 90 degrees, 180 degrees, whatever it may be. Whatever the step angle that you have to require, that it can be rotated by the rotor with respect to the step angle what we design. Next, it is given by theta s is equal to 360 by n into nr. This is nothing but n is equal to or n or m. It is the number of phases. How many number of phases are giving towards the motor? That is, if you consider the stator is having that four phases. If you consider that is four phases, so this is four pair of poles or eight pole stepper motor. Or if you consider six pole, there comes towards a three phase, four phase, six phase. What about the number of phases you are giving towards the stator coils? That it should be depend upon the machine or motor. Therefore, with respect to the number of phases and number of rotor teeth, how many number of rotor teeth are given towards the silicon steel structure of the rotor? Therefore, with respect to the structure of the rotor, therefore that it should be giving the theta s is the step angle. Okay, here the above equation is applicable to variable reluctance stepper motor. For hybrid stepper motor, it is given by there is a different types of motors we observed. That is a variable reluctance stepper motor, permanent magnet stepper motor, and also hybrid stepper motor. These are the three important motors. But some other motors are also having, that is the disc type, and also single phase stepper motor, single phasing stepper motor, and the disc type stepper motor. These are the some of the applications. And if you consider the three main classifications of the stepper motors are variable reluctance stepper motors, which can use that a minimum reluctance path to rotate the rotor. And next one is a permanent magnet. The rotor is also designed with a permanent magnet rotor. Not in place of the silicon steel structure of the rotor in a variable reluctance motor, stepper motor, is changed in the permanent magnet rotor stepper motor. Here, with respect to variable reluctance and also the permanent magnet stepper motors, by combining these two, we designed another one is the hybrid stepper motor. What are the nothing but the features of these two variable reluctance and stepper permanent magnet stepper motors are having, or combinedly gives that the hybrid stepper motor. Here, there is a small difference with respect to the variable reluctance and also the hybrid stepper motors of step angle, calculation of the step angle. That is, theta s here it should be m number of phases into nr, but it should be 2n. It should be changes into 2n, 2n into nr. Nothing but the number of phases are multiplied with 2 times here. That is the main difference of a hybrid stepper motor. Nothing but for the variable reluctance stepper motor, for permanent magnet motor, there is no difference. This is the formula for finding of step angle. But the hybrid stepper motor, there is an addition of 2 multiplication with the 2 value. That is the difference. Here, next one. What is meant by the resolution? Resolution is defined as the number of steps per revolutions, and it is given by z value, which is equals to 360 by theta s. Theta s is nothing but a step angle. Here, what is the resolution? Here, the rotor is rotating, but it should be rotate. It is rotating in a step manner. That is a number of steps. How many number of steps are being served? Suppose if you consider an example of a motor, 360 degrees of the displacement of the motor. If you consider the steps must be how many means? If the step angle is 60 degrees, for suppose 60 degrees is the step angle. How many steps that it should be rotated by the rotor? 60 into 6, that is equal to 360. Therefore, the requirement of the steps that it should be for a 60 degrees step angle motor is to be what? How many? 6. That is the that is nothing but the resolution. Resolution is defined as number of steps per revolution. How many number of steps that it should be considered for the complete revolution of 360 degrees. That is nothing but 360 by, if you consider 60 degrees, 6 number of we are getting. That is nothing but the resolution. The resolution can be very high, if you go for more value also, more value. Nothing but if you consider, we are considering that theta s is equal to 60 degrees. If you consider 6, here if you consider 6 degrees, theta s is equal to 6 degrees means 360 degrees by 6. How much? 60 degree, 60 value. 60 number of rotor steps that it should be moved. Therefore, the resolution changes. The resolution is next. Now it should be 60 revolutions. Sorry, 60 steps per revolutions has been taken in the stepper motor. That is the difference. What is meant by the stepping rate? It is nothing but the number of steps completed per second is called stepping rate or stepping frequency. This is also important one. The number of steps completed per second is called. When we calculate it with respect to time, nothing but if you consider this much time, suppose 1 minute. In 1 minute, how many number of steps it should be rotating by the rotor, the motor? The number of steps completed per second is called stepping rate. Is also, or it should be, or it called as a stepping frequency. This is nothing but a stepping frequency or stepping rate. Okay, next hold position. This hold position is nothing but corresponds to the resting position of the rotor of an excited motor. This is one of the definition. Next one, detent position. Here, detent position is nothing but this position corresponds to the position of the rotor of an unexcited motor. Unexcited motor. Detent position means previously detent torque we discussed about the detent torque. Detent torque. What is the detent torque? Here again I am telling that if we are having that four pair of poles or 8 poles are nothing but four faces. We are giving the four faces A, B, C, D, A dash, B dash, C dash, D dash. Like that, 8 poles we are having in the motor. But if you consider when you supply given towards the A phase, towards the stator coil of A phase, so what should happen with respect to the supply given towards the A phase? Therefore, there is an excitation provided towards the coil. Therefore, that A coil behaves as electromagnetic property, behaves as electromagnetic property consisting and produces the magnetic field. Here, if you consider after rotation of the rotor, actually for A phase excitation, the rotor is under 0 degree condition. Suppose if you consider that is under 0 degree condition. If you consider here next the degrees of the rotation is to be 6 degrees of the motor. Suppose therefore while sorry not 6 degrees it should be 60 degrees. Next to exit a B phase, A phase is switched off and B phase is getting to switched on. Therefore, turn on. Therefore, what should happen? B phase is getting excited. Here, immediately after switch on or turning on the B phase, B coil, that it should be excited. But A coil has been switched off, but there is a magnetic field property within the coil. That is nothing but the position corresponds to the position of the rotor of an unexcited motor means due to the magnetic field existence with a small value of A phase, the rotor that behaves as nothing but which opposes to rotate also whenever B excited, immediately after B excited. Therefore, a small torque is also required to bring towards the B phase rotation of the rotor towards the B axis, B phase axis. That is nothing but the detent torque or detent position. Next, what is meant by stepping error? The stepping error is equal to the difference of actual step angle minus theoretical step angle by theoretical step angle. This is nothing but the stepping error. Next one, what is the positional error? We are also getting some of errors as precision. There is no accurate precision can be produced by these motors. Why? Because when you go for step angle of a very low values, suppose in 10 degrees, 6 degrees, or lower than values, then these are called precision motors. Nothing but the speed is to be controlled accurately or precisely for at this position. Nothing but 6 degrees. Yes, at this position, the motor will be controlled or stops. Again, it will be starts. Again, run. Again, starts. Again, stop. Like this. Nothing but due to all these conditions, we are getting some errors also. Here, the positional error, which defines that this is the maximum range of cumulative percentage errors taken over a complete revolution of the rotor. Nothing but if you consider cumulative percentage errors taken over a complete revolution, This is considered as for all the 60 degree of the step angle, total 60 steps we are getting on the rotor complete one revolution. Therefore, for all the 60 steps, there is a small error. For 6 degrees of again it should be changing towards 12 degrees, 6 plus 6, 6 12, 12 plus 6, 18, like that. By changing all these degrees values, what should be happen? There is some error. There is some error. Yes, exactly, some error is should be occurring. Why? Because these are all considered the practical machines or practical motors which we are working. There is some error due to here the total errors of the 60 step angles we will consider in a complete one revolution. That is nothing but the positional error. The next one is the holding torque. It is the maximum torque that can be applied to an excited motor without slipping the rotor from the equilibrium position. Holding torque. This is also important one. Here, it's the maximum torque that can be applied to an excited motor without slipping the rotor from the equilibrium position. Nothing but here A phase is excited. S, the rotor is rotated, and after B phase is excited, and then again the rotor is to be rotated. To be rotated. To be rotate means here what should be happen? Without any why? Because these all the motors are consisting the loads. With respect to the load, the motor has to be worked. Depend upon the load only, based upon the load only, the motor can be worked, continuously worked. While these are the conditions we are happening in the motor, here the holding torque, maximum torque that can be applied to an excited motor without slipping the rotor from the equilibrium position. Nothing but rotor cannot be moved towards backward or forward. Nothing but the rotor can be whenever B phase is excited. Yes, to align this same axis of the B phase, therefore it doesn't changes towards the unequilibrium position. Nothing but it doesn't changes towards or oscillate towards oscillations. Exact position can be occurs. That is called nothing but the holding torque. And the detent torque, detent position of the detent torque we discussed, that is nothing but the same. This torque is present only in permanent magnets and hybrid motors only, not for the variable reluctance motors. And next one, start stop mode. And next one, slewing mode. These are all the different modes of operations. If you observe, first if you observe the start stop mode, this is a mode of operation of a stepper motor in which the second pulse is applied to the motor only after the rotor has attained the steady or rest position due to the first pulse. If you understand this point, if you understand, when you are giving the pulse towards the switch circuit, therefore current is to be moving towards. Whenever there is a pulse at turn on period, up to that point only, it should be start. And again, after that, it should be becomes towards the stop mode. Yes, why? Because there is no pulse. Why? Because there is no switch turn on position. Like that. Next one, swing mode. In this mode of operation, the second pulse is applied before the motor has attained the steady state position due to the first pulse. In this mode, the motor cannot be stopped immediately by stopping the applied pulses. But also the motor cannot be started in this mode. This is nothing but the swing mode. Next one, pull-in torque. Pull-in torque, pull-out torque. This is also important. Pull-in torque corresponds to the maximum torque developed by a stepper motor for a given stepping rate, the start-stop mode of operation. These are comes under start-stop mode of operation without losing the synchronism condition. Nothing but there is no loss of synchronism or losing of synchronism. Rotor cannot be delayed or cannot be overcome. Why? Because it can be aligned in the same position of the stator axis. Stator axis. Nothing but alignment of the position with respect to the excitation given by the coil to the coil. That is nothing but the pull-in torque. Next one, pull-out torque. It is maximum torque developed by a stepper motor for a given stepping rate in the swing mode without losing synchronism. Swing mode and also the start stop mode. These are the two values we occur here. Next one, pull-in rate. It is the maximum stepping rate at which the stepper motor will start or stop without losing synchronism against a given load torque. Next one, pull out torque, pull out rate. Pull out rate corresponds to the maximum stepping rate at which the stepper motor will slew without losing synchronism. These are the comes pull in and also pull out comes under these two modes of operation. So start stop and also sleeving. Next one, synchronism. Synchronism means one-to-one corresponds between the number of pulses applied to the stator and the number of steps through which the rotor has actually moved. One-to-one means that is this explains that if you consider three-phase motor, the three-phase motor is operated with how many switches? Six switches. If four-pole four-phase means it should be eight switches. Why? Because one is to be entered towards the coil. Suppose A coil we are having. A coil means not only the A only, we are having A and also A dash. Why? Because it is a concentrating series connected coils. These are the concentrating series connected coils which are placed in the stator. Therefore, whenever the current is to be moving towards the A, that is behaves as a north pole, and A dash that behaves as a south pole. Like that. Here, what is the synchronism that tells me is each and every time. Suppose six switches we are having S1, S1 to S6, S1, S2, S3, and S4, S5, S6. If you operate any one of the phase, suppose S1 is connected towards the A phase, that is A coil, and A dash coil is having that within the A phase. A dash coil is connected towards suppose S5, suppose S4, S4 or S5, whatever it may be. Okay. Therefore, these two switches are turned on. S1 and S5, S4 are turned on. Next S2 and S5, S3 and S6. Suppose, for example, we are considering any, at each and every time interval of time, we have to operate two switches. First switch S1, suppose second switch another one. Like that. Two switches you have to operate. Therefore, with respect to the two switches only, the phase can be excited, A phase. Next, we have to change towards the B phase. To B phase can be to be exited next onwards. What should happen again and again? Another two switches should be operated. Like that. While giving the pulses towards the switching circuits, through switching circuits, then only the switches can be closed. Like that. Okay, that is nothing but there comes under the synchronism operation. Next one, mid-frequency resonance, and it is the point of at certain input pulse frequencies, the rotor torque drops a low value. This phenomenon is called mid-frequency. Nothing but at certain input pulse frequencies, the motor torque drops to a low value. Suppose this comes under the mid-frequency resonance. And next one, response range, a range of stepping rates in which the stepper motor can start or stop without missing steps is called response range. Nothing but each and every time synchronism definition is also comes towards the response range also. Same meaning. Why? Because first two switches are activated, turn on, and next A coil is excited. Next B coil is excited. Next two switches are to be turned on. Nothing but without missing the steps to rotate the rotor. 6 degrees means exactly 6 degrees to coming the stator rotor. After that 6 plus 6, 12 degrees. After that 12 plus 6, 18 degrees. If not means 6 degrees first step. Second step is to be 10 degrees. Actually, we have to exactly step is to be 12 degrees, but it should be reduced with 2 degrees means there is a change. Nothing but it is not a responding it not accurately. That is nothing but the response range of the stepper motor. Next one, you have to these are also observe start stop stepping rate, and also these are ramping. When the motor starts from rest with load, it cannot follow the pulses. Also, a motor running in slewing mode cannot be stopped suddenly by drawing the pulses. For bringing loaded motor to desired speed, it must be accelerated for stopping it. But all these are considered under loaded condition. Loaded condition of the motor, not only off-load condition. It is these all are considered under on-load condition. Next, if you observe the static characteristics of the stepper motor, here these are the characteristics which are drawn for torque versus the step angle. The step angle are considered on the x-axis and torque on the y-axis. Therefore, how the characteristics of the stepper motor, if you observe here vary the load torque and find the corresponding displacement. Here, if you observe, this is the point. The angular displacement is measured by varying the load torque and find the corresponding displacement. Here, the variation of this displacement is plotted against the torque. Here, if you observe, initially, if you observe, this is the torque, this is the holding torque. T suffix H is nothing but the hold torque. Okay, now, oh, okay, hold torque, it is nothing but up to that point there is no torque. Here, initially, with respect to the step angle, if you observe, the sorry, the torque value is to be increasing like this. Up to this point, that is nothing but whenever if you exited A phase coil, therefore rotor rotates. Whenever rotor rotating means the torque is rising like this. Up to this point, nothing but theta s is the step angle. Theta s is nothing but the step angle. Theta m is nothing but the maximum step angle. If you consider that is theta s is the point. S step has been taken. Therefore, the torque value like this. Okay. Next onwards, it should be right zero. It coming towards the zero means there is the A phase is unexcited. Next B phase is to be excited. Like that. Here this is the important one. Theta s up to the theta s point step angle, the torque value is to be like rising like this, and this is nothing but the holding torque. Up to whenever the step angle reaches, that comes towards the holding torque. After that, there is no torque. Okay, the rotor stops up to here, up to this point. The rotor stops. Okay, these are nothing but the characteristics, the torque angle characteristics of the stepper motor. Next, if you observe the dynamic characteristics, how the dynamic characteristics here, with respect to the dynamic characteristics, we observe the torque values of pull-in torque and also the pull-out torque. Pull-in torque is different and pull-out torque is different. Pull-out torque is nothing but when it pull-out torque occurs means there is a losing of synchronism condition. There is a losing of a synchronism condition. Nothing but A phase is excited. Yes, the rotor is rotated with 6 degrees. When B phase excited, the rotor is again 6 degrees. That is total 12 degrees. Like that, it is continuously rotating with respect to the step angle of 6 degrees. Suppose. Therefore, there is a process. Nothing but there is a condition of synchronism condition. But if you consider, if you consider, if you, if you, con- if you consider the torque value of a pull-out value means here under this condition there is a possibility of losing the synchronism, unsynchronism condition. Here the dynamic characteristics of a stepper motor consists that nothing but here when it is running or about to run, pull-in and pull-out torque characteristics are called dynamic characteristics. Pull-in characteristics is also known as the starting characteristics. Pull-in characteristics is also called as the starting characteristics. Here, this curve refers to the range of frictional torque against which a motor can start without losing any steps. This is the curve up to C point. Starts and torque value is to be okay. After that, what should be happen? It should be drops towards nothing but with respect to the stepping frequency. You have to consider that is nothing but pull-in curve and next one pull-out torque. The pull-out or swing characteristics is the plot of relation between the friction and torque and the maximum pulse rate at which the motor can be synchronized. These are the two curves of to behave in the synchronism condition, to not behave in the nothing but pull-out torque which comes under losing of the synchronism condition. Next one, open loop control system. What about the open loop control system? Here, if you observe the block diagram of the open loop control system of a stepper motor, for the stepper motor, this is nothing but the stepper motor. For the stepper motor, we are provided with a power controller, which is provided with a DC supply. And again, an amplifier. What about the signals to be amplified with a certain range, required range, but towards the power controller? That is also given with the DC supply. And next one is a logic controller. That is provided with step input and the direction of input. Direction of input is to be, suppose it is rotated forward direction, yes. Next it is to be rotated in reverse direction, yes. There is a possibility of a clockwise direction rotation and also counterclockwise direction of the rotation also. So like that, if at what speed does it require to sorry, at what direction does it rotate the motor, that it can be depends upon the direction of input given here. This is the input. Next one, step input. Step input means here what type of pulses we are giving, okay, towards the logic and also nothing but if it is positive pulse, if a no pulse means a zero, positive pulse means a one. One is nothing but turn on. Zero means it is a turn off. If you observe in the previous sessions of truth table, in the truth tables, there is ones and zeros. Ones and zeros means if you consider that one is a turn on position and zero is nothing but a turn off position. Turn off position. Okay, like that, these two are considered. Okay, these are provided towards the logic control. Nothing but we are providing with the four switches. Suppose there is a eight pole. Eight pole means four switches. S1, S2, S3, S4. Therefore, first you have to start S1. Yes, next S2. Next S3. Sorry. Next, if you observe the step input towards the logic controller. The logic control consisting of a truth table. Here, truth table, and these are connected towards the amplifier. Nothing but ones and zero signals are provided towards the amplifier, which amplifies the signals and provide towards the power controller. So nothing but the power controller consisting of the switches. Power switches, nothing but what are the switches of suppose for a four phase, eight switches were discussed. Those four switches are operated. Suppose those are switches of IGBTs or the MOSFETs, like the normal thyristors switches also of a power electronic. Why? Because the stepper motors of ratings are having that high. If you go for highest ratings, means we choose these like IGBT switches. Why? Because to control the switches means through any gates, through any gate controllers. Therefore, we go for an IGBTs or thyristor switches or SCRs. Like the switches we are placing in the power controller with respect to the signals giving towards the switches, nothing but in a sequence manner. Suppose if you consider three phase, it is a three phase stepper motor. Therefore, six switches we are providing here. Six switches, total six switches. At a time, we are operating any two switches. That is 1, 6, 2, 4, 3, 5, like this. Okay. Therefore, these switches are operating and giving supply towards the stepper motor. Based upon the sequence of the switching pulses giving towards the circuit only or towards the power controller only, the stepper motor operates. Next one, that is nothing but the truth table. If you observe, these are the truth table of R by B phases. R by B phases are given of 1, 2, 3 steps. First R phase and also next R phase will be observed. Next again like this. These are the truth table, and this is nothing but a logic controller. JK flip flop, as in flip flops we are including in this logic controller. That is the JK flip flop. This is nothing but JK flip flop. Okay. These are the pulse generators which are giving signals to pulses towards the flip flop. अब biscuit and next one, power switching circuit. The power switching circuit, if you consider this is the power switching circuit, which are this circuit is included in the controller, power controller. The circuit is placed in the power controller. This is nothing but what I told that IGBT switches which are placed here with respect to the coils of R by B. Okay, here Right? Each and every time, one phase to be turned on means R phase on, next Y phase, next B phase, like that. Okay, and this is nothing but the closed loop control of a stepper motor. Here, in a closed loop control of a stepper motor, a new command for exciting a phase is given only after the previous command is fulfilled. Okay, the first step takes more time due to inertia of load. Another step, another motor, and the motor. The command for second step is given only after completing the first step. Okay. Next, if you consider, this is nothing but this is the closed loop system, which is having the position sensor of a, if you consider Hall effect sensor. The stepper motor is giving nothing but positioning sensor senses the speed or torque value of the stepper motor, and these are giving signals towards the OR gate, from the OR gate towards the counter, and towards the digital comparator. Here, the comparator compares the steps, required number of steps we are giving. Suppose 60 number of steps we are giving towards the motor. Suppose this is the reference value. Okay. Next, this positioning sensor senses always at at each revolution how many steps are taken, and these are giving here, and both are comparing here. If it is equal means there is no error signal. If it is not equal means there is an error signal towards the translator, and these translates and gives to the amplifier, and again this and amplifier output has been provided towards the power converter circuit. Okay, like that, we have to giving the signals towards the stepper motor. This is a four phase. This is a four phase stepper motor. If you consider in the block diagram while you are observing, it is a four phase. Previously, it is a three phase. Next one, if you observe a microprocessor based control of a stepper motor. This is also important one. If you go for a microprocessor based control means we are providing that a controller, that is an 8051, okay, 8081, 8051. These are the different types of microcontrollers we are giving, placing. Here, the microcontroller having that 40 pin circuit. Within the 40 pin circuit, we are having different options of voltage inputs, and also the stepping rates, and also the reference signals which are providing towards the direction of rotation, and also these positioning sensors given towards the step angles, stepping rates. These are all the signals which are provided, which are included within the controller. That is, example, if you consider an 8051. From this microprocessor or the microcontroller memory, we are including a program. You consider program which are included in the microprocessor. What at what stepping rate that rotor is to be rotated. Like this, all these kind of parameters we are included in the program. Depend upon the program, we have to operate it. Okay, the motor can be operated. Therefore, the microprocessor is the requirement to maintain an automation. Therefore, which is connected to the opto isolator. This is an isolator circuit. Next one towards the drive circuit. Towards the stepper motor. I hope all of you understand about these characteristics, and also closed loop, open loop, and control system or control of the stepper motors. In the next sessions, we discuss some more topics on the stepper motors. Thank you.